Hi, my name is Churned. I'm the VP of Product at Kaskada, and I wanted to personally welcome you to DataCon LA this year and our booth. We sponsored this conference because we believe in all of the technical talks and conversations that are going on, and we are excited to participate. If you're here and you're watching this video, it means that you're either interested in the product or you're here for questions, and we're busy with someone else at the moment. So stick around for just a few seconds and we will definitely get to any conversations you might want to have. I do have a little bit of content for you. So just in case you only have just a minute, stick around and I will show you a brief demo as well as a few pieces of information. So Kaskada is the first feature engine with native time travel, and we'll be giving live demos in the booth as well as answering any questions you may have about how this might work in your company or to solve some of your problems. Here are the times where we're scheduled to be here. So it's during the breaks of all the sessions across the 3 days. But additionally, if you just want to register interest and have a one-on-one conversation, not to worry, click the button and we'll reach out. We have a couple of additional times and a couple of additional guests. So we have our CEO and co-founder who'll be here after any of the talks, as well as myself and Ryan Michael, one of the engineering leaders on our team. If you're here as a data scientist, you might want to come at this Saturday time at 4:40 after our first talk. If you're a data engineer or builder, you'll probably want to come on Sunday after the second talk that we have. And just to put a face to a name, here are a few folks. This is Ryan Michael, the engineering leader I mentioned, giving the talk on overcoming data infrastructure limitations, and our CEO and co-founder, Davor Bonacci, who will be joining me in my talk, as well as Ryan in his and the keynote in the morning on Saturday. These are the talks themselves. So if you're interested in our point of view, the lessons that we've learned building a system like this, or you just have questions about how to solve some of these problems yourself, please come to these sessions. Data scientists come to the creating and operating ML models from event-based data, data engineers and builders. That overcoming data infrastructure limitations is for you. So you're here to learn about Kaskada. So let me tell you a little bit about it. Kaskada is the first feature engine with native time travel. And if you think about that for a moment, what it means actually is we are providing a compute platform for data scientists to do feature engineering with the ability to travel back in time to compute any feature at data-dependent points in time. So what are some examples of this and why do we care? Data science can have very specific impacts on our revenue. And Kaskada uses event-based data, structured event-based data, to power models like personalization, recommendations, and fraud alerts. Kaskada does not do natural language processing or image processing, etc. But what the models that we support, what we actually do, can have major impacts on the bottom line. And you're trying to adapt faster and launch sooner so you can rapidly improve your business metrics and respond to a changing world. When you modernize your existing tech stack and data platform, you'll be able to deliver immediate time savings and increase the amount of data usage and data products that are served across the organization, including these machine learning models. And the truth of it is, your existing models are going stale. More and more stakeholders are requesting new models, and you're trying to update the ones that you already have in production, trying to keep up with this impact that Amazon can make on their personalizations. And your data scientists really want to explore new features. The problem is that they're limited with the data and the tools that they have today. In order to explore directly from raw event-based data, structured event-based data, they need a self-serve computation so that they can build training data sets and confidently serve those features in production faster. To get a little more specific, I decided to use gaming as an example. Gaming companies have lots of event data, and they're adding new platforms that generate even more data, things like live operations or live ops. They're exacerbating the changing environment by adopting valuable tools And the promise of these tools are to allow the business, the product managers, the game owners, to change, update, and make improvements to a game without having to release a brand new version, which is amazing. And from a business standpoint, you can benefit by engaging and retaining users, increasing the lifetime value of an individual user. From a data standpoint, however, you're creating complex changing environments over time. But is it worth it? We know that versus segmentation alone, at least the studies show, that behavioral segmentation has a 3 times higher revenue impact. On top of that, behaviorally triggered message delivery, so the right message at the right event, has a 7 times higher impact. And then after that, personalizing that content at the right moment with the right behavior has a 14 times higher revenue impact. But like I said, from a data standpoint, you're creating changing environments. You're having segments that have one treatment versus another segment that has a different treatment. And you're running campaigns with start and end dates over time, switching 1, 2, 3, 4 levers at a time. It makes it impossible to analyze your historical data unless you can look at the actual events. What did a user see? Did they see that particular ad? Did they see that particular level up? And what happened after the fact? Which means that the teams today are running these campaigns live and then analyzing the facts a couple of months later after there is a clear A/B test winner. And so trying to guess what levers are important isn't particularly efficient. But if you add data science and you add machine learning to this, you can decrease the amount of pressure on the teams to perform, right? You're gaining a bunch of time back. Kaskada allows you to compute specific examples at specific points in time because you have access to the raw events that actually occurred, whether or not a user saw a level up, whether or not they actually purchased that item. But today, you likely care about maybe one of the levers, the first-time user experience, the top of the funnel, driving the initial engagement. And after you solve that problem, maybe you're able to build a data pipeline that allows you to hand label or automatically label the events to learn from for first-time user experience. But tomorrow, you're likely going to need to do more. You're going to have to optimize time offers, like a day lagging harvest calendar. You're going to have to figure out what the in-game power-ups should be. And for each of these points in time, your model needs a different data set to learn from. What about the first time a session was logged in? Or the first missed day? When a player loses? When a player gets stuck and too much time has passed? When a player only has 5 moves left? Each of these events, each of these conditions define different points in time for different users, for different possible training examples. And Kaskada connects to your event-based data to test a series of hypotheses on historical data to better inform which of these particular features are predictive. When should you serve your events? What should your behavioral segmentation be? And how can you customize? So that's a lot of words. Let me show you a little bit of a diagram. So Kaskada is a compute platform. You have Kaskada there in the center. You've got the feature definitions. You're writing your features as code. And independent of the features, you're doing time selection, the prediction time and the label time to compute your historical feature values. But that means that you can share those feature definitions in production. You can actually go from your iteration and your exploration and discovery to actually serving your results in a production environment. All you have to do is compute those features at a time of now. So let me give you a little bit of a demo. If you're a data leader or you are a business leader, you're going to want to schedule a one-on-one conversation with us because the demo I'm about to show you is specific to data scientists, because I've been a data scientist in the past and I'd love to just geek out a little bit on the nitty-gritty details inside of a notebook. But if you're a data scientist, stick around. I'd love to show you a few things to get you started. And then have you click try it now below. If you have any product feedback, like I said, I'm the VP of product. I'd love to hear from you. So let me just switch on over. Okay, so first, after you sign up, head on over to our doc site. We have a nice selection of developer docs here. We have a Hello World notebook. So if you have questions like, how do I get my data set up? How do I create tables? How do I map my information? This notebook's for you. Just give it a run through once you have your credentials. But today I actually wanted to show you a specific notebook. This is our customer retention problem. It's similar to the gaming scenario, where your purpose is to retain a user, retain an account, retain a subscription based upon their behavior in the past. And we know that this type of model is different than others. Different in a way that you don't already know what may be predictive, and you're never going to have the entire feature set available. You may have spent years trying to solve this engagement and retention problem with machine learning. And part of the reason for that is that you have different data sources in different places, and you haven't been able to join them together. Your feature engineering infrastructure is holding you back. So if you're able to connect directly to structured event-based data like click streams, transactions, event logs, error logs, and other data with timestamps that's structured, with Kaskada, you can explore new features instantly and serve those features confidently in production in minutes and weeks and not months, quarters, and years. So I went ahead and I've installed Kaskada and I've run through this notebook one time just to speed up this demo. So as you know, what data scientists love about Jupyter is the nonlinear exploration. You've already got an existing workflow where you're able to do discovery, cleaning, modeling, etc. And I don't want to mess that up. So Kaskada's provided a Python client library and a couple of extensions that are going to help actually work directly in your workflow today. So I've already set up a couple of tables. You'll notice these tables have a time column and an entity column. It's just letting Kaskada know how to actually efficiently process the data. We need to know exactly what entities you're going to be predicting and how to order the data in order to actually sequentially walk through those events and produce historical values. So when you go to do your first type of exploration, maybe you're looking at a specific user. In this query, this percent fennel is just letting the cell know this is a fennel query, it's a decorator from our fennel magic extension, and everything after it is a simple query, a simple question. In particular, these queries are not persistent. So you can make changes in a single cell and run it over and over and over again, and you're not doing anything negative to your production data sets or anything in anyone else's experimental environments. So here we'll notice that we see 24 rows for this particular user. And we have a bunch of columns of information about these transactions. And for the members table, I just pulled up the whole table here. We see that it's pretty messy. And we'll still need to do either some data cleaning or with Kaskada, some event selection, some time selection. Tell Kaskada when to compute the events, what data is valid, what you should use. And we're still going to have to do some of the things that we normally do in our workflow, like visualize this information to know even what type of events we should select. So we're going to go ahead and show some of that. It's a simple query here. I'm using pandas and NumPy and matplotlib to show a histogram. And this is just a basic fennel query, the plan days, the payment method ID, a date, and an expiration. And as I scroll down, you'll notice there's 1.7 million rows in that simple query. And Kaskada returns the queries in data frames. So you can manipulate these with the libraries that you're used to today. So if I want to explore the columns in my data frame, or I want to plot one of these columns in a histogram, it's super simple. So I don't know about you, but when I'm in my workflow, I often have this matrix of maybe 4 or 5 graphs wide and maybe 10 graphs long in order to see different scatter plots to understand relationships and correlations with the data. It's perfectly fine. Keep those. Use all of your favorite libraries when you're doing your data exploration. But when it's time to build up your query, you're going to want to start with Kaskada. And your data may already contain a label without needing to compute But Kaskada doesn't require this. And in fact, we often recommend that you want to find a target feature that you can compute. When a customer eventually churns, you think your subscription end date is at the end of the year. That may not be when the business actually counts that as a churned customer. It may be 15 days after they expire, or a specific day of the month when the books close and your customer success team actually has time to win them back. So instead, if you can define that target feature as something in code, we can compute those labels at specific points in time. But I'm getting a little ahead of myself. So first, let's build up a query. You're going to want to set up your prediction time. And this can be data dependent in order to do your event selection. You'll start with one criteria and build up the time selection by viewing your data, adding more time selectors, and just kind of iterating, adding line after line. So for that messy data set that we saw, we may want to say, I don't want all of my transactions. I just want them if the payment plan days are greater than 0. And I only want to include the events that happen before the known expiration. So all of these lines up here are allowing me to build up the model context. What events do I care about? What events am I going to use in the future in order to make a prediction at that point in time? So I have a set of clean transactions that are based upon those conditions. Next, I'm going to define my label time. This can also be data dependent. You can use business logic. When does that customer really churn? Is it at its expiration date, or is it 30 days later? And what you'll see here is that we're taking the features that are computed at the prediction time, and we're shifting forward in time to label them. And then we're defining what those labels are. We want to know what's the target feature. And here we're saying, if we're comparing 2 transactions, if I go 30 days past the expiration, have I had another transaction? And if I haven't, this customer has churned. And if I have, then they haven't. So the true and false here. And so now it's time to define my features. And I'm showing this as a linear process. It's not really. For each time that you're adding one of these conditions, you may want to just show all of your data and some computed set of features. You may not know what features are important yet, and you want to just show all of the columns. That's perfectly fine. But once you're ready to start computing features, you can start building up operations. Things like the duration of the subscription or monthly active users, etc. And so as you define and iterate on these features, you can leave that time selection static, or you can iterate on it as well as you're looking at your graphs. Below, I can see that these features are computed at their prediction times, as well as their labels 30 days later. And if I wanted to change this particular time that the labels are computed, maybe I only want 7 days later, and I rerun this cell, I can instantly get back another labeled data set within seconds. So 12 seconds later, I've been able to compute a brand new label data set across 1.7 million rows. I have 1.7 million training examples and labels. So to summarize, data scientists want to explore new features from raw event-based data through self-serve computation of training data sets and confidently serve those features in production. And all I've shown so far is the historical feature value calculation. But what about getting to production? You can use any library to train the models. So I'm not going to go into a deep dive on model training and selection or computing precision or balancing weights. That's a whole nother step in your process that you can do after this. But what I do want to show you is the data and machine learning engineer workflow. What we know is that they hate Jupyter. The nonlinearity that was so beneficial as a data scientist turns into a nightmare. They have to reconstruct history and figure out what we did in order to re-implement some of these features and see if it's viable to get to production on production data. But with Kaskada, you can bridge the gap to production. Kaskada connects directly to the event-based data available in production, and the queries that we were able to run in the notebook doesn't change that data at all. Data scientists can instead define the predictor features used to power the training data sets and create a view that allows these features to be shared as code. Then data and ML engineers can call Kaskada to compute the same features at the time of now in production. And so Kaskada provides production-grade targets, such as Redis, for feature and model serving. So let me show you how that works. When I'm in Kaskada, all I have to do is create a view, and I'll delete the existing one so that I can create this new view. The expression itself is what is saved, and this is what's persistent. Once a view is created, it's available across multiple environments using these credentials. And you can find the features or the feature sets defined in these views by doing a list of your views. And so the code itself and any comments in your code are shared. And a data engineer can then run this view, query Kaskada again with new data, but the same feature definitions to populate a feature store. If you're going to compute simply the new or incremental values, we have an incremental value API for that, or you can recompute data at any point in time for audits or historical reasons. And data engineers don't need to use Jupyter. And so now a data engineer on your team can use Kaskada's APIs and these persistent views containing the feature definitions to compute new values on new data in various standard formats and serve them in production. So that's all I have for you today. Kaskada is the first feature engine with native time travel, and I'm really curious to know what you think. So if you have a moment, scroll down, click Try It Now, try out our APIs, try out our developer docs, and let me know what you think for the first time using time travel for feature engineering.